In a lab in Manchester, a student pressed a single fingertip against a sheet of clear plastic. A machine dragged the plastic sideways and measured exactly how hard his skin gripped it. He did it with the ridges. Then he flattened them out and did it again. What came back broke a belief that had stood for a century. The thing everyone swore gave us our grip was quietly working against it. You have been told the same story your whole life. Your fingerprints are there to help you hold on. The ridges dig in, they catch, they grab, like the tread on a tyre or the studs on a boot. It feels obvious. You grip the world with your hands, and your hands are covered in tiny ridges, so the ridges must be for gripping. Case closed. That explanation is more than 100 years old, and for that entire century, almost nobody checked. Here is the strange part. When someone finally measured it, your fingerprints did the opposite of what you were promised. They did not tighten your hold on the world. They loosened it. So how did we get the story so wrong for so long? Part of the answer is that we were busy looking at fingerprints for a completely different reason. In the 1890s, a scientist named Francis Galton became obsessed with them, and he proved something remarkable. Every fingerprint is unique. No two people share the same pattern, not even identical twins, and the pattern you are born with never changes for the rest of your life. That discovery turned your fingertips into the most reliable signature in the world, and it built modern forensics. But notice what every one of those investigators was asking. They wanted to know what your fingerprints could tell us about who you are. Almost no one stopped to ask the simpler question, what are they actually for? It seemed too obvious to bother testing. The lines were on the gripping part of the hand, so the lines were for gripping. That was the answer in the textbooks. That was the answer everyone repeated, and it sat there, untested, for 100 years. The man who finally tested it was a biomechanist named Roland Enos at the University of Manchester. He studies the physics of living things, why a tree does not snap in a storm, why a stalk of grass can hold itself upright, and he had a simple itch of a question that, somehow, no one had ever scratched with a real experiment. If fingerprints are for grip, then a ridged finger should grip better than a smooth one. So is that even true? To find out, he and his student Peter Warman built a rig that slid a sheet of acrylic across a human fingertip and measured the friction at every moment. They pressed harder. They pressed softer. They changed the angle of the finger and the width of the sheet. They watched precisely how much the skin held on. And the numbers refused to behave, because what they found did not just fail to support the old story. It pointed somewhere else completely, toward a reason fingerprints exist that has almost nothing to do with holding on. To understand it, you have to understand one quiet fact about your own skin. Your skin does not grip like a rock. It grips like rubber. That sounds like a small detail. It changes everything. When you press two hard, solid things together, stone on stone, steel on steel, the friction between them depends mostly on how hard you push. Press harder, hold harder. The exact shape of the surface barely matters, but soft, rubbery materials follow a different rule. For them, friction depends on how much surface is genuinely touching. More contact, more grip. And this is the trap the old theory walked straight into. Look closely at a fingerprint. It is a tiny landscape of raised ridges and sunken valleys. The ridges touch the surface. The valleys hang above it, touching nothing. So the instant you carve ridges into a soft fingertip, you do something no one expected. You lift part of the skin away from whatever you are holding. You shrink the contact. Enos and Warman measured exactly how much. A ridged fingertip meets a smooth surface with about a third less skin than a flat one would. 33% of your fingerprint is, in effect, floating. It never touches the thing you are trying to grab, and if your skin behaves like rubber, and it does, then less contact means less friction, and less friction means less grip. The ridges everyone praised as nature's grip pattern were, on a smooth surface, making your hold weaker. Have you ever wondered why racing cars run on smooth, treadless tires? On a dry track, a bald tire grips far better than a grooved one, because every inch of rubber is pressed against the road. The grooves on an ordinary tire are not there for dry grip at all. They have one purpose: to push water out of the way in the rain. A smooth tire on a wet road would skate off the surface. The tread rescues it. Hold that thought. Your fingertip is a soft, rubbery surface covered in tiny grooves. A racing slick grips a dry road best when it is perfectly smooth. So why, across millions of years, did our hands keep the grooves? The answer is that fingerprints were never tools of force. They are tools of information. Think about what your fingertips can do that the rest of your skin cannot. You can drag a finger across a table and feel a single grain of sand. You can tell silk from cotton with your eyes shut. You can find a hairline scratch on a pane of glass that you cannot even see. That sensitivity is not just a gift of soft skin. A huge part of it comes from the ridges. In 2009, the very same year as the Manchester experiment, a team of physicists in Paris led by Georges de Brégy decided to test this directly. They built an artificial fingertip. One version had a smooth surface, the other had fingerprint-like ridges, and they dragged both across textured surfaces while recording the vibrations inside. The ridged version was not slightly better, it was dramatically better. As the ridges rolled over fine texture, they amplified the vibrations and tuned them, sharpening exactly the frequencies that your most sensitive touch receptors are built to feel. Deep in your fingertips sit nerve endings called Pacinian corpuscles, and they are tuned to vibration, to a flutter that repeats a few hundred times a second. The ridges work like the strings of an instrument, turning the faint roughness of a surface into a clean signal your brain can read. Slide a smooth fingertip over fine texture, and the signal is a muddy smear. Slide a ridged one, and it rings out clearly. Just how sharp is this sense? In 2013, a team led by Lisa Skedang put a number on it. A sliding fingertip they found can feel a single ridge only 13 nanometers tall. That is a bump so small it is closer to the size of a large molecule than anything your eyes could ever resolve. Your fingertips are reading the world at a level of detail your vision cannot come near. So the lines on your fingers are not a clamp, they are an antenna. And once you see them that way, the rest of the evidence falls into place. Consider the koala. A koala's fingerprints are so close to ours that, under a microscope, they have genuinely been confused for human prints. Koalas did not evolve to swing through the canopy like acrobats. They spend their lives gripping branches and, above all, selecting and stripping eucalyptus leaves with their hands, slow and delicate and precise. Fine handling, fine feeling. The same pressure that shaped your fingertips, showing up again in a creature that split away from our branch of life an enormous span of time ago. There may be a second job hidden in there too. Remember the tire treads, draining water. Enos suggested the valleys between your ridges might do the same thing, wicking moisture away so the skin can still touch a wet surface. The way treads keep a tire gripping a flooded road. And there is a stranger clue tucked inside your own hands. When you soak in a bath, your fingertips wrinkle. For ages we assumed that was just skin swelling with water. It is not. That wrinkling is switched on deliberately by your nervous system, and researchers at Newcastle, among them a scientist named Tom Smith, found evidence that those wrinkles help you handle wet objects more securely. To be fair to the old idea, ridges might still help a little on rough, natural surfaces, a branch, a stone, but even there, the picture is not kind to it. When Enos looked, fingers seemed to grip rough surfaces worse, not better. Whichever way you turn the evidence, the same conclusion keeps surfacing. Your hand is built around water and texture and information. It is barely interested in raw, brute grip at all. So look down at your own fingertips for a moment. Really look at them. You have been carrying a precision instrument on the end of every finger for your entire life, and someone told you it was a clamp. Every time you feel for a switch in a dark room, every time you check whether a counter is wet or dry, every time your fingers read a texture a half second before your eyes catch up, that is the ridges doing the one job they were ever shaped for. Not gripping the world, reading it. There is a person who proves this better than any experiment. Someone reading Braille runs a fingertip across a field of tiny raised dots and pulls whole sentences out of them, at speed, in the dark. No grip is involved at all. It is pure reading, by touch, through the ridges, and on the other side, people who lose their fingerprints. Some are born without any. Some wear them smooth through certain kinds of work, do not lose their grip. They go on holding things perfectly well. What fades is quieter than that, the fine edge of touch, the sharpness of the world beneath their hands. We spent 100 years certain that these ridges were how we cling to things. We taught it to our children. We printed it in our textbooks. The ridges were never there to help you hold the world tighter. They were there to help you feel it.